Good morning everyone. So today let's discuss on the generalized monocouple system, and we will try to discuss today so previously we have seen in case of a monoatomic chain how the wave is propagating. We have seen that where is the band gap is coming and all those things. So and also we have studied the mass in mass system, and also negative stiffness, and we have also seen the inertial amplifier. But if you think, all those things are belong to a class of a system, that is the monocouple system. So what is primarily a monocouple system means? So if you see a monocouple system, that basically tells you are having, so whatever is your unit cell, like let's say this is your unit cell. So that unit cell, like one unit and the other unit, they are connected, like unit n and n plus 1, they are connected by a single degree of freedom. So connection between consecutive units is 1 DOF. So single DOF, it's maintaining the connection. So that we can call it as like a monocoupled. So here the two unit cells are coupled using a single degree of freedom. That's a monocouple. That's a basic monocouple system. Now here you may have your unit cell like this, like that's a mass in mass unit cell. You may have the unit cell like this type. This is inertial amplifier type unit cell. Now, and this may be also like this way as well possible. So that's maybe inertial amplifier. Then you may add a spring in between. So so that is inertial amplifier IA. This is your mass in mass. You may have a negative stiffness also. So in negative stiffness we will not have that black one. So this is your negative stiffness. But primarily if you see, they all are connected to the next unit cell or the previous unit cell by a single degree of freedom. That's why these all are belong to the class of monocouple system. Now once we are talking about a monocouple system, now the question comes that once we have these many types of the monocouple system, can we get a generalized monocouple system? Yes, we can get a generalized monocouple system. And how that generalized monocouple system looks? So that generalized monocouple system unit cell looks like this. So if you see, this is a basic unit of the IA. Now what people are doing, then they add the spring mass, so that become your negative stiffness. So already IA is there, negative stiffness is also get attached with it, and you can also attach that hub resonators here. So now you see that this portion is your mass in mass, or maybe you can call it negative mass, because we have seen in case of the mass in mass, at some frequency band we can have the effect, our effective mass becomes negative. Okay, then if you think in the top part we have a negative stiffness. That spring actually creates a negative stiffness. Now if you think that this portion and this link is creating the IA, inertial amplifier. So this combines all the three different forms, and we can call it at a IA NM NS system. Negative inertial amplifier, negative mass, negative stiffness system. So that combines all the three different forms of the general units of the metamaterial. So it's called it as a generalized monocouple system. And now if we can able to solve that generalized monocouple system, we can able to get all the properties. So let's see how this generalized monocouple system we can able to solve and how we are able to getting that. So let's first take the basic unit cell of a generalized monocouple system. So if I draw it, let's write. So this is my K2. This is K2 by 2. This is M2 by 2. This mass. This mass is M1 by 2. This mass is Ma. This is M3. This is K3. This is K1. So if we have this way, and we can also able to name the nodes. So we can call it like one. So maybe node numbers I should write it in the different color. Maybe 1, 2, 8, 7, that is 4, 5, this is 3, and this is 6. So all 1 to 8, all the nodes are there, like 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now our job is try to write all the equations. So first we start writing equation for this resonator. So resonators attached to the main mass. If I try to see that equation how it will work, that will be in the node 2 and node 7. So if I try to do that way, then how it is coming? M2 by 2 U7 double dot plus K2 by 2 into U7 minus U8, that should be equal to 0. On the other hand, if we also write it, M2 by 2 U2 double dot plus K2 by 2 into U2 minus U1, that should be equal to 0. Okay, that two equation we got. Now again, if we start writing for node 4 and 5, these two nodes. First one we wrote it for these two nodes. We got that. Now node 4 and 5. So this is 5 and that is 4. 4 is here. 4. 4 and 5 if we are writing, then how we can able to get it? 4 and 5 will come like M3 into V or W actually. It is different, it is not U because it is moving in the perpendicular direction. So whatever we are taking in the perpendicular direction, we should write it in that. So U3W5, M3W5, well, M3, mass is M3, M3W5 plus your K3 into W5 minus W6, that is U. Similarly, M3 W4 plus K4 into W4 minus W3, that should be equal to 0. Or that's W or Z, whatever. So maybe we can write it Z actually. Z6 and Z3. So these are Z. The displacements are Z. And this node was 4 and this displacement is W4 actually. Okay, so this way we can get that. Okay, now what about the node 3? Now, so we see that 4 resonator node we are completed, like resonator 2, 7 and resonator 4 and 5 we completed. And obviously we can understand, it is needless to say that these resonators are not getting coupled with the main equation. When they will coupled, but their degree of freedom should not be present in the transferring one, because in transferring one only the transfer happening from 1 to 8. 1, 8, again they are in 8, the previous units 1 will be get connected, so the periodicity will be applied only on 1 and 8. That's why it's a monocouple system, because periodicity is applied only in the 1 and 8. Other nodes are not connected to the next or previous unit cells. Okay, that's like an important point and we need to remember that. Fine. So now if we think, what about the node 1 is doing? Now node 1 and 8, where are you write node 1 and node 8? Or maybe before the, okay, node 1 and node 8. So how it is doing? So node 1, node 8, so M1 by 2 into U1 double dot plus K1 into U1 minus U8, K1 into U1 minus U8 plus K2 by 2 into U1 minus U2 should be equal to 2Fn cos phi. I'll come, what is the Fn cos phi? So Fn cos phi, if you see, like you are taking, like suppose if I take this portion, you just take that. So once you cut this, so you will have Fn, because that rigid link you have to cut, so that Fn terms will come into picture. So you will get it like this way. And for the node 8, similar thing, plus K1 into U8 minus U1 plus K2 by 2 into U8 minus U7 equal to minus 2 Fn cos phi. That we can able to get if we are equating node 1 and 8, node 1 and 8. Okay, so we can see that we can able to calculate here this. So from the node 2, node 7, node 4 and node 5, node 1 and node 8, we can able to get all the equations, these equations. Now what is remaining here? Remaining nodes is 6 and 3. Now if we try to write the equation for the node 6 and node 3, then what can we write? Node 6 and node 3 equations will be, so it will go like this way. Here it will be Fn, so node 3 will be coming here, and you can see that for node 3 it will be Ma into Z double dot, Z3 double dot plus K3 into Z3 minus W4 should be equal to minus 2 Fn sin phi. So that's become my equation for Z3 double dot, Z3. So Z3 is going like this, Z3, so we can able to get it. Similarly, we can also able to get Z5 also like this way, that is K3 into Z6, that is Z6 minus W5, that should be equal to minus 2 times Fn into sin phi. Okay, we got that two equations. Now what is my objective or goal? Now if you see, we should try to condense all the equation in terms of node. So these all equations we should try to condense, like this set of equation, this set of equation, and this set of equation we should try to condense. Okay, so if I try to write here, what can we get? We can get here, like we can write it, U7 should be equal to K2 by 2 into U8 divided by m2 by 2 omega square plus k2 by 2, not plus, minus k2 by 2. I think they were wrong. Okay, we can get it like that. So my u7 can be written in terms of u8, and similarly u2 can also be written in terms of u1. So u7 or u2 we can able to write in terms of u8 and u1. Okay, now from here also we can easily able to write like w5, we can write it as like k3 into z6 divided by k3 minus m3 omega square. So this is 5 comma 4 in terms of 6 comma 3 we can able to write. So what we can see that now these w4 and 5, these w4 and 5 can be coming here, w4 or 5, and we can again, so this equation we can able to write it like ma z3 double dot plus k3 into 1 minus k3 divided by k3 minus m3 omega square into z3 should be equal to minus 2 fn sine phi. So what happening here? Here we can able to write z3 in terms of fn, or opposite, that fn in terms of z3 we can able to write it. Okay, no problem. So fn, so here we can say that we are writing fn in terms of z3. Okay, now we have also another interesting equation, that is the kinematic equation. Like we have this rigid link, and this rigid link is moved here, and this one is going up. So this is my z3, this is my u1. So now this one is becoming like this, and then it is coming like this, because it was like this. So basically it actually coming back like this, so that is minus u8. This is z3. So how can we write it? So we can write that z3 equal to z6 equal to minus z3 into u1 minus u8 divided by 2 tan phi, divided by 2 tan phi. Now if you see how this thing is working, so like your u1 minus u8, and so that once that 3 is going up, you will have in this way. Fine. So we can able to write the equations like this. Fine. So now once we got that, and previously we have seen, we can write fn equal to some function into z3 or z6. So now fn can be written as some function into u1 minus u8 divided by 2 tan phi. We can able to write it. Okay, because we can substitute that one here. So from here what can we write exactly? Fn should be equal to 1 divided by 4 into tan phi into sine phi into k3 minus ma omega square minus k3 square divided by k3 minus m3 omega square into u8 minus u1. That we can able to get from the previous one. So like you can see here, my Zn, Z3 we can able to write it like this. So we can substitute it back there and we can able to get Fn in terms of like this. Okay, so once we are getting this one, so that Fn cos phi we can able to write it 1 by 2 tan square phi into k3 minus m3 omega square minus k3 square divided by k3 minus m3 omega square into u8 minus u1. That we can get. So I can call this full term as like ln. So I can call it ln into u8 minus u1. So now if I try to write our main equation, like my first equation back, if I try to write it, what should I write? So my first equation was m1 by 2 u1 double dot plus q1 into u1 minus u2 by u1 minus u8 plus k2 by 2 into u1 minus u2 equal to 2fn cos phi. Now 2fn cos phi equal to is ln of u1 minus u8. You can see here, sorry, u8 minus u1, u8 minus u1. Okay. So and also u. So if I try to take, so that's the equation I can get, and the next equation will become m2 m1 by 2 u8 double dot plus k1 into u8 this plus k2 by 2 into u8 minus u7 should be equal to minus ln u8 minus u1. Okay, that way we can able to get that two equations. So this equation can also be rewritten like this way, that m1 by 2 u1 double dot plus k1 plus k1 minus something, yeah, k1 plus ln into u1 minus u8 plus k2 by 2 into u1 minus u2, that should be equal to 0. So that's the same equation, I can write it like this. So this equation can also be written m1 by 2 u8 double dot plus q1 plus ln into u8 minus u1 plus k2 by 2 into u8 minus u7, that should be equal to 0. Fine. And what are my other two equations? Other two equations are staying m2 by 2 into u2 double dot plus k2 by 2 into u2 minus u1, that is 0, and m2 by 2 u7 double dot plus k2 by 2 into u7 minus u8, that is equal to 0. So here if you see now what happened, what are the parameters left with me? We have u1 double dot, we have u1, u8, u1, u2, we have u8, and here what are there? u2, u2, u1, u7, u7, u8. So we have primarily here u1, u2, here u8, u7, here also u2, u1, here also u7, u8. So now you can also able to condense that matrix and you can write. So if you condense the matrix what we can get? We can able to write. So here, what we can do? We can write it U2 equal to K2 into U1 divided by K2 into U1 divided by 2, and here also half minus M2 omega square plus K2, so half cancel out, so you will get it K2 into U1 divided by K2 minus M2 omega square, that is U2. And similarly this will be also true for U7, and here it is U8. So now if I substitute that two equation again here as well, then what can I get? So then this equation will be coming M1 by 2 U1 double dot plus Q1 plus ln into U1 minus U8 plus K2 by 2 into 1 minus K2 divided by K2 minus M2 omega square into U1. That should be equal to 0. Got that? And this equation will become M1 by 2 U8 double dot plus Q1 plus ln into U8 minus U1 plus K2 by 2 into 1 minus K2 by K2 minus M2 omega square into U8, that is equal to 0. Okay, so this equation we got. So now once we got that two equations, so can I write it in the matrix form? That is, sorry, not that big. Wait a minute. M1 U1 double dot U8 double dot, so these two terms consumed, plus Q1 plus ln, and if I try to simplify this term, let's see how it comes. K2 by 2 into K2 minus omega 2 m square minus K2 divided by K2 minus omega 2 m square. So this cancel out, so what we will left with K2 m2 omega square divided by 2 into K2 minus m2 omega square. That we will left with. Okay, so this minus K2 m2 omega square divided by 2 into K2 minus m2 omega square, that will come here. Now how much will be coming here? Here you will have minus Q1 plus ln. Here you will have minus Q1 plus ln. Again you will have Q1 plus ln minus K2 m2 omega square divided by 2 into K2 minus m2 omega square. That multiplied by U1 and U8, that will be equal to 0, 0. Agreed? So we got it in this way. Now we can also write it in that directly, like we can, as we are already taking the what to say, like already we have done it into frequency domain, so no meaning to keep that also in the time domain. So we can just put it like half of m1 omega square plus Q1 plus ln minus K2 m2 omega square divided by 2 into K2 minus m2 omega square minus Q1 plus ln minus Q1 plus ln, and half of minus half of m1 omega square plus k1 plus ln minus k2 m2 omega square divided by 2 into k2 minus m2 omega square. That should be equal to that multiplied by u1 u2 u1 u8, that is equal to 0 0. That we can able to get. So that's become my dynamic stiffness matrix. Okay. So once we get the dynamic stiffness matrix, after that what can we do? So we got the dynamic stiffness matrix in this manner. So my dynamic stiffness matrix dy into u should be equal to my force. Okay. Now here one thing is important, we can also notice here it is not always required to put the 0. You may have force at 1 and you may have force at 8. So I can put it force at 1, force at 8. It's not at all changing anything. If I put force 1, force 8, it can also be staying there, not a problem. So what we can get? Now if I try to find out the receptance matrix. So what is the receptance matrix? Receptance matrix is something, you can think it like a flexibility. Stiffness matrix telling how much displacement you like, suppose if you are apply for getting a unit displacement, how much force is required, that we can tell from the stiffness matrix. On the other hand, for applying a unit force, how much displacement will be happening, we can able to get it from the receptance matrix or the flexibility matrix. So flexibility matrix R of omega is, or the receptance matrix, basically like inverse of dy. So that how we can able to get? So that is the inverse matrix. So if I say that this is nothing but alpha LL, alpha LR, alpha RL and alpha RR, we can say it like this way, that matrix will come. Just obviously that is a 2 by 2 matrix. So 2 by 2 matrix, if we do the inverse, it will be also 2 by 2 matrix. And I am just defining like alpha LL, alpha LR, alpha RL and alpha RR by that 4 terms. So here alpha LL, if we are trying to calculate, then alpha LL will become, so alpha LL will be equal to alpha RR, because you see that these two matrices are symmetric. So now if you remember A, B, C, D, if you have a matrix like that, and if you do the inverse, then it will become like, if you have a matrix A, B, C, D, now if you take the inverse, then it will become D, A minus B minus C divided by its determinant. That's the thing. So now if you think, if A and D, now if A equal to D, then what will happen? They will become same after inverse, and B and C were also same. So like you are having like A, D, A, D, so it is like A, B, B, A. You are inverting that one. So it will be A minus B, 1 by A square minus B square. That way the things will come. So here also you can think that same thing happening. 1 by D, like that, determinant of this multiplied by omega square m1 by 2 plus k1 plus k2 by 2 plus ln plus k2 square divided by 2 into omega square m2 plus k2. That is coming in my alpha LL. And alpha LR equal to alpha RL, that also we can get it. Determinant of dy, that is k1 plus k2, k1 plus ln, that we can get as a alpha d. So these two we can get easily, these two terms. So from here Now the question comes that, okay, once we get that receptance matrix and all those, so what we can do it from here? So for the unit cell, any monocouple system, the force displacement relationship we can able to rewrite like this way. So we can write the force displacement relationship as dl dr, like the left side. So you can think that that is the unit cell. So I am applying the force here FL, and it has a displacement dl. Force here is Fr, it has a displacement dr. So this is equal to FL Fr. Okay, so this is alpha LL, alpha LR, alpha RL, alpha RR. Okay, now if we try to recall why we are doing that, our objective is to find out how the band structure is going to look, where will be the attenuation peak, how many attenuation peaks are coming, so that we try to actually find it out. So for that we are doing this one. So now if you think here there is a periodicity, so dr will be equal to e to the power of I mu times dl, and what will be Fr? Fr will be minus e to the power of I mu times Fl. I think you recall that why Fr is with a minus sign, because once we are having the displacement, that it is basically the continuity is getting maintained. On the other hand, once we are having the force, then we have to balance, the force need to be balanced. Force is not the continuity, force need to balance. So we will have that negative sign here. So now if I just substituting these two things here, then what can I get? So now if you think we are having dl dr, that is equal to alpha LL, alpha LR, alpha RL, alpha RR times FL Fr, and other two condition is dr equal to e to the power of I mu times dl, and Fr equal to minus e to the power of I mu times Fl. So if I start substituting that full thing, what can I get? What will be my objective? So I will try to go to either of that and try to see that how the equations are coming. So if I try to just substitute it, so first equation we can write dr will be equal to alpha LL into FL plus alpha RL into Fr. Now I substituting this one again. So alpha LL into e to the power of I mu times alpha LR into FL. Okay, this is dl equal to okay. Now on the other hand, if I write dr, that will be equal to alpha RL times FL plus alpha RR times Fr. So similarly, what can we write? Alpha RL minus e to the power of I mu times alpha RR into FL. Okay, fine. Now, so that's my equation 1, this is my equation 2. Now if I think, and sorry, maybe it is, you just think it, this is equation 3, equation 4, this is equation 1, equation 2. So now if I put in the first equation, then what can I say? dr, that is alpha RL into e to the power of I mu times alpha RR into FL should be equal to e to the power of I mu times alpha LL minus e to the power of I mu times alpha LR times FL. Okay, combining, like once we are substituting 3 and 4 into equation 1. So FL can be cancelled out. So what can I write? Alpha RL minus, or what we can do, we can pre-multiply with e to the power of minus I mu. So e to the power of minus I mu times e to the power of minus I mu times e to the power of I mu will become 1. So alpha RR should be equal to alpha LL minus e to the power of minus I mu times LR. Okay, so what can we write? We can write that e to the power of I mu plus e to the power of minus I mu times alpha RL equal to alpha LL plus alpha RR. So what we have seen in the last time, like also you are doing that, like A B B A matrix inverse. If you do, you will see that it will be A minus B divided by A square minus B square. So basically what happened? These two terms are same, they are same, and these two terms are also same. So you can say that alpha LL equal to alpha RR and alpha LR will be equal to alpha RL. So what happened? Here I can just substitute it to the alpha RL instead of writing alpha LR and alpha RR. Alpha RL and alpha LR I am just writing alpha RL, and here it is this, so we can also write it 2 alpha LL. So alpha RL. Now if I try to think that what it is coming here, so can I say that it is becoming cos mu? 2 cos mu equal to 2 into alpha LL divided by alpha LR. So cos mu will be equal to alpha LL divided by alpha LR. That we can get. Okay. So this cos mu equal to alpha LL and alpha LR once we are getting. Now what is alpha LL, what is alpha LR? Alpha LL is also basically a function of omega, and alpha LR is also a function of omega, like maybe that is g of omega. So what it is actually giving, so we are getting cos mu equal to alpha LL divided by alpha LR, which both are function of omega. So we can get it in terms like f of omega divided by g of omega. So this is nothing but your dispersion relation. If you think, we are getting mu in terms of omega, what we have done before also, but this is a different way of looking the same thing what we have done previously. But this is in the approach of, like, we are making the receptance matrix, and from there, if we are using the theory of the monocouple system, we can able to derive it in this format. Now here, this actually tells something very, very important. What? We can able to find the property or the nature of these things. So let's see how it will actually work. Or we can just assume it as x as well. So cos mu equal to or this. We can assume, okay. So now if we assume this, again we can write it e to the power of I mu plus e to the power of minus I mu, that is equal to x. Or this thing can be written e to the power of 2 I mu plus 1 should be equal to 2x into e to the power of I mu. Now if I think e to the power of I mu equal to, let's say, a, then what can I write? I just assuming this one, so I can rewrite this as like a square plus 1 minus 2xa will be equal to 0. So what is the solution of it? So its solution, we all know that solution is a equal to, so this is basically a quadratic equation, that is a square minus 2xa plus 1, that is equal to 0. So what is the solution of, like, not x here, a here, that is equal to minus b, that means plus minus root over of b square minus 4 ac, minus 4 ac, so that will be 1, because here also coefficient is 1, here also coefficient is 1, so minus 4 ac divided by 2a. So we can get it x plus minus this. Okay. So now if you think, what is your a? A is basically e to the power of I mu, so that is plus minus 2 root over of x square minus 1. Agreed? And what is x? X is nothing but function of omega. So here if I take the log ln of e to the power of I mu, then what can I get? Ln of x plus minus root over of x square minus 1. We can get it like this one. So basically, so this will gives me I of mu, that will be nothing but ln of x plus minus. Okay. Now if we think that mu is equal to something like alpha plus I beta, alpha plus I beta, so I mu will become minus beta plus I alpha. So we can say minus beta plus I alpha, so to be equal to ln of x plus minus root 2 x square minus 1. And what is alpha here? If you think, once we are assuming this one, I hope all of you remember that this is nothing but e to the power of minus alpha plus I beta, and that actually with the terms of x, and this is telling that how wave is getting decayed or attenuating, what is the correlation between the one side to another side. So if you think that way, then it is coming I alpha into e to the power of minus beta. So minus beta is doing what? Minus beta is decaying the full thing, and e to the power I alpha is primarily a propagating thing. So e to the power I alpha is propagating, e to the power I alpha is propagating, and e to the power minus beta is decaying. So we can able to get that solution like this manner. So here we can also say, okay, so we can get it like this way. On the other hand, if we try to see, we can also able to write like cos of mu equal to, like what we got here, like alpha LR, alpha LL divided by alpha LR. So that can also be thought as like 1 minus omega square me divided by ke. So what is that? Me is the effective mass divided by the effective stiffness. So we can able to write our dispersion relationship like this way as well. So cos mu equal to 1 minus omega square me divided by ke. So here me and ke both are the function of omega, so there the omega can also go. And more interestingly, this can also be written as thought as like a rational polynomial. So we can able to write it like this way also, like r of omega square divided by this. So this is the way we can able to express the frequency part of the dispersion relationship as like a rational polynomial. Okay, so now if we can able to write it as like a rational polynomial, so what happened, like we can express the frequency part of the dispersion relation like a rational polynomial. Okay, so once we are writing it as like a rational polynomial, then what can we say? Now that gives several interesting things. So we can think that first foremost point, that what is the range of cos mu. So now the real range of cos mu is basically plus minus 1, minus 1 to plus 1. So in that range, if we are thinking, what are the boundaries for that polynomial? Boundaries of the polynomial will become this divided by this equal to 1, and 1 minus 1 plus r of omega square divided by q of omega square, that should be equal to minus 1. So these are the two boundaries. So these are the two band boundaries, because in the propagation band, what happened? Mu is only equal to alpha. That I beta part is basically 0. I beta part is basically 0 in that case, or it's opposite actually. Sorry, means you understood that like that cos mu should means for a real mu, that cos mu should be lying between plus 1 to minus 1. So we can say that this thing is lying. So we can say that in the propagation band, that mu should be real. So now if the mu should be real of the cos mu, it should be real. Then what? Then we will get this thing, and now what? We will have r omega square equal to q of omega square. And in this case, what we are getting? We are again getting another form of equation, that is this should be plus q of omega square, that should be equal to 0. We are getting these two equations. Okay. So if we are solving these two equations, we can able to get the band boundaries. And for different metamaterial system, we can able to calculate what is the r omega square, what is the r and what is the q. So once we are getting the r and the q, we can easily able to write down this thing, and we can able to find out what are the band boundaries. So band boundaries means, suppose if you see the plot, like it goes up, then it goes here, and then it goes like this. So these things, so these frequencies, like where, like in this region is like a propagation band PV, this region is like attenuation band AB, and this region is again propagation band PV, and what happened? And then again, once it reach here, again you will start getting the attenuation. So again it comes the attenuation band. So these boundaries, like if I just see like F1, F2, F3, these band boundaries we can able to calculate if we are solving these two equations, and if we are looking at these we can able to find it out. So this gives that interesting point. Okay, any doubt up to that? Okay, so we see that once we are going like this way, so this, by solving these two equations, we can able to solve the basically the band boundaries. And also one interesting thing is that where we are able to getting that peak, we can able to find out. Now if you see, in case of a mass-in-mass system, like once we are having like this type of like a mass, then there we were getting something like a single attenuation. So there is a single peak we are getting. And why you are getting a single peak? And that peak is corresponding to the internal resonance, like suppose for example if we think that internal mass is m2 and internal spring is k2, then this is coming root over of k2 by m2. So root over of k2 by m2, in that frequency we can able to get a drop, and that is happening in case of the mass in mass system. But now think in case of IA and MNS, where we are having this type of structure and different degree of freedoms are coupled with each other, we may have multiple peaks and they may get interacted, they may get coupled with each other. So what it exactly and where the peaks are, what is the cause of that peak, and where the band boundaries should be, that's become a very important question, and that we can able to solve by expressing that dispersion equation, in form of a rational polynomial. That's actually enable you to solve in that way. So if you think we can write that, like we have our cos mu equal to 1 plus r of omega square divided by q of omega square. So r of omega square can be written like this way, that r3 r square cube, or maybe 6, plus r2 omega 4 r1 omega square plus r0. Okay, similarly q square can be written fine. Now here that order is like a very important parameter. Like what is the order of that express polynomials? Now if you think in case of a monocouple chain, what was happening? In case of a monocouple chain, you have the expression yes. So that was the scenario for a monocouple chain where everything is just going like this. So in that case, what is my r omega square equal to only I can say r1 omega square plus r0, and also here r1 is basically my m and r0 is 0. Fine. And what is the q omega square? Q omega square is basically k only. So that means q omega square is q0 and q0 is k. So once this type of thing is happening, then where my boundaries are lying, then you think you are basically solving this thing, that r omega square equal to q omega. So r omega square equal to q omega, if you solve r omega square, that is r1 omega square should be, or maybe m omega square should be equal to k. Sorry, I made a small mistake. It should be minus. So here at r1 equal to minus m omega square. So you see that first equation was r omega square should be equal to q omega square. So that equal to 0. Sorry. So this gives me minus m omega square equal to k square. So what is the omega square? Omega square will be minus k by m. So that's not possible, because that gives the imaginary. And what is the next equation? R omega square plus 2q omega square should be equal to 0. That means minus m omega square plus 2k, that is equal to 0. So omega square equal to 2k divided by m. Sorry, not root. So this is the condition. And if you see, that's very correct also. We always able to see that this goes up to 2 times. Like if we are writing it in terms of like omega divided by omega n, where omega n equal to root over of 2 root over of k by m. So we can always see that this goes up to this stage. So we can see that these equations nicely show the boundary for this case. Now let's see what happened for the machine mass. So in case of machine mass, if we think we are having this one, so internally it is m1, it is externally k1. So what is my cos mu equal to? So cos mu equal to, we know that 1 minus me omega square divided by ke. Now ke is here is k only, so not a problem. What is me? Me is basically m1 into 1 plus m2 by m1 into 1 minus eta 2 square. So that one is m1 plus m2 into 1 divided by so if I try to write that full thing in the form of m by r, how can we get 1 minus m1 plus m2 k2 divided by k2 minus m2 omega square into omega square divided by ke divided by k. Okay, so that will come. So what can I write? And if I write like, okay, that k2 by m2 means omega square divided by k2 by m2, if I write it like eta square, then we can write it cos of mu equal to 1 minus m1 by k into 1 plus theta into 1 minus theta 2 square. Okay, that we can get. Now what is my RE then? So, and we also know that we can able to express it RE omega square divided by K, R omega square divided by Q omega square. So what is Q omega square? So Q omega square will be 1, or here omega is become first of all eta. So if I just try to rewrite it little bit, so m by k, then 1 minus eta 2 square, 1 minus eta square, maybe you just think 1 minus eta square plus theta. Okay, so what is my, so now I can write it 1 minus m by k into 1 plus theta minus eta square divided 1 minus eta square. Fine. So I can also write it 1 plus m by k into 1 eta square minus 1 plus theta divided by 1 minus eta square. So what is my, and this thing, and we also know that cos of mu can be written 1 plus r divided by q, r eta square by q eta square. So what is my r? My r is like r I can say like eta square minus 1 plus theta, that's my r. And what is q? Q is k by m into 1 minus eta square. So how can I write? R eta square, that is equal to r1 eta square plus r0. So what is my r1? R1 will be equal to 1, and what is my r0? R0 will be equal to minus 1 plus theta. What is q and eta square? Q eta square will be k by m, and yes, q eta square k by m, q by m minus eta square plus k by m. So now what can we get? q1 equal to minus k by m, and q2 will be equal to k by m. So from here, if we try to check that where the q is higher, where the q of omega square is becoming 0, that means in that point your receptance is very, very high, so that it's not going to flex, it's become flexible. So when it will become 0? Once this thing is equal to 0, so you can able to get that way.